Hello and welcome to my tutorial on the modern periodic table. So I'm using the textbook today because I would like to show you some pretty pictures while I talk. So the modern periodic table is like this. This is a period and these are groups, and they're all arranged according to similar chemical properties. We'll find out how they're organised now. So, in the modern periodic table, elements are arranged in order of their atomic numbers. Each horizontal row is called a period. Elements often show trends and gradual changes in properties across a period in the table. These trends are repeated across each period. The repeating pattern of the trends is called periodicity. Each vertical column is called a group and contains elements with similar properties. The periodic table is the chemist's way of ordering the elements showing patterns of chemical and physical properties. So, the key areas in the periodic table is what I showed you just now, and the green ones are separate metals. The elements of green are separate metals from non-metals, and it's this line that indicates the differences between covalent bonding and metallic bonding on the periodic table. So if we go and look at this picture, gradually as you work your way down group 4, it turns from a non-metal, a covalent compound, carbon, all the way down to a metal, lead. So as your electron structure varies like this, as it gradually gets bigger, the patterns tend to repeat themselves, and this is why they're organised. The elements are organised in a certain way. So chemical reactions involve electrons in the outer shell. Any similarity in electron configuration will be reflected in the similarity of the chemical reactions. Similar elements are placed in vertical groups. This is a key principle of the periodic table. So elements within a group have atoms with the same number of electrons in their outer shells, and this explains their chemical behavior. This repeating pattern of similarity is caused by the underlying repeating pattern of electronic configuration. So we go back to the table, then if you look at each one, the electron configuration gradually increases like so. Goes along like that, and we zoom out again. We can move on to the next part now, and ionization energies. So the ionization energies rely on three things: nuclear charge, distance from the nucleus, and electron shielding. So they gradually increases up to neon, and then all the way down again to argon. If we go back to the periodic table, so as we drop to each and every period, the ionization energy increases because of the extra shell of electrons. So when you get down here, it gets really hard in order to remove an electron from these bad boys. But most of these are radioactive anyway, so they're going to decay subatomic particles anyway. But that's precisely the point. It's very difficult to remove electrons as you get further down the periodic table. So, with the exception of helium, neon, and argon, which their ionization energies decrease. But just before you reach those elements, the ionization energy is at its highest point. So, if you look at here, the atomic radius is decreasing, and the first ionization energy is increasing because of the greater nuclear attraction on the shells and less electron shielding, and the number of protons is increasing because. the atomic radius is decreasing, so the proton number must be increasing. It's a common thing. So now we'll look at the number of shells increasing. If shielding increases, then the first ionization energy decreases, and that's what happens down a period of the periodic table. So now we'll look at boiling points. So from metals to non-metals, this is across one period. It's like a sort of illustration of what it looks like. Now if we look at period 2 and period 3, giant metallic structures have strong forces between positive ions and negative delocalized electrons, and they have metallic bonding. But when you get to giant covalent structures, they have very high boiling points, and then when you get to gaseous atoms like nitrogen and fluorine, they have very simple molecular structures and weak forces between the molecules, so they must have van der Waals forces and very, very low boiling points compared to the giant covalent bonds and the metallic bonding. So in terms of melting point from sodium to aluminium, if you have more ionic charge, the greater the attraction, and therefore the number of outer shell electrons released increases. So if you have more electrons, then the boiling point is going to increase, but only if the metal is a solid. If it's not solid, then the ions will be mobile, and well, if the ions are mobile, then they're not going to have that attraction anymore. You would have melted them, and they would be free to conduct electricity if you wanted them to conduct electricity. So we're looking now at the group 2 elements and how they have redox reactions. So the physical properties of them is that they have reasonably high melting and boiling points, and they are light metals with low densities, and they form colourless compounds. So they basically react in this way. Group 2 elements are oxidizing reactions. Each atom loses 2 electrons from its outer S subshell to form a 2+ ion. So the metal forms a 2+ ion plus 2E minus. You could have determined this if you looked at period 2, knowing that all the elements in that period form 2+ ions, and the 2E minus is just a formality to say I've removed 2 electrons in this equation. The decrease in ionization energies down the group 2 is an important factor in this process, so we're going to look at that later. If we look at the electron configuration and their first ionization energies, they are gradually decreasing as we're going down the group. So if each group 2 metal has lost 2 electrons, and in the S subshell, the highest energy level subshell, so the S subshell is highest energy level subshell, when the metals react, the 2 outer electrons are lost. The first ionization energies decrease down the group. This is reflected in the increased reactivity down the group. But radium does not fit in with the trend because it's radioactive. But we're not going to talk about radon because I love radon too much, and we need to only concentrate from beryllium to barium for OCRAS chemistry. So if we react with oxygen, we get 2 calcium plus O2 makes 2 calcium oxides. So if you apply oxidation numbers, we're going to do that now. Then if calcium is plus 2, excuse the atrocious pen, that is minus 2, then therefore 2 of them, so 2 oxygen is minus 2 minus 2, and plus 2 plus 2. So no 2- ion has formed like in previous tutorials, but rather it is cancelled out completely to 0. But elements on their own are always 0. So well done if you spotted my careless mistake. Elements are always 0, but they have both reduced and oxidized. This is why it's called a redox reaction. So calcium has lost electrons and oxygen has gained them. Sorry, calcium has lost electrons and oxygen has gained them. I cannot draw, so we'll leave it and we'll look at the reaction with water now. So if we apply oxidation numbers to this particular one, elements are 0 and the 2H is +1 when it's bonded to an oxygen, and calcium is always +2, OH is -1, and H2 is always 0. So calcium has been oxidized and hydrogen has been reduced according to that one. So the final thing to note is that only one hydrogen atom in each water molecule has been reduced, and the other hydrogen atom does not change its oxidation number. So this is because magnesium reacts very slowly with water. As you move further down the group, each metal reacts more vigorously with water, with calcium fixing and popping like some very, very crazy soluble paracetamol tablet, as you will find out if you ever do a chemistry practical. So for the reaction with calcium with oxygen, we'll just go back to the examiner tips now. These are the two equations that could be asked in the exam, so if you write these down and try and learn them, then it wouldn't hurt too much in order to remember them. So only two simple equations, and these two ionic equations are just background of how we got to our final products, calcium hydroxide plus hydrogen gas. So this is like what happened in between the intermediate stages, if you will. So you tend to see these reactions as calcium is always a solid. So using state symbols here is key, as I tend to forget my state symbols because I just tend to balance the equation. So always write your state symbols first. Work out that calcium is a solid, then work out that it'll be aqueous and then gaseous, and then balance your equation so you don't forget like me. So now we'll move on to the group 2 compounds and their reactions. So as the solubility increases for magnesium hydroxide, their alkalinity increases as well. So barium is the most alkaline and the most soluble as well. And looking at the ease of the thermal decomposition, it's the same trends. As you go down the period, the carbonates are easy to decompose. So a simple decomposition equation is Mg magnesium carbonate makes MgO plus CO2. It's the default. In theory, I could write X CO3 plus not plus equal X oxide plus, alright, CO2 there. So it's any where X is any one of the group 2 elements, including radon, but we're going to ignore radon because I love radon too much, and the OCR examiners don't care because the properties are slightly different. So the properties of the group 2 elements in a nice summary table. So these are nice for your notes. The bonding is metallic and has a giant metallic structure, strong forces between the positive ions and negative electrons, and it has 2 plus ions whenever ions are formed, and it makes it by that equation there. As it is a reducing agent, it loses electrons and it increases down the group reactivity. Now we'll look at this very nice reaction of calcium in its compounds, but it is exactly the same for any other group 2 metal. Just replace it with magnesium or strontium or barium, and you're sorted. However, calcium plus oxygen is calcium oxide, and calcium oxide plus HCl is calcium chloride, and then you thermally decompose it to make calcium oxide, and so on and so on. That's probably even better to summarize this entire page of notes. So calcium hydroxide is used for farming, to neutralize acid soils, and magnesium hydroxide is used to relieve indigestion. There is a very, very nice exam question on magnesium hydroxide. I will guarantee that you will rip your hair out. I know I did when I had a go. So hopefully when the exam questions come up, you won't rip your hair out. So now we're moving on to group 7. Group 7 is from fluorine all the way down to iodine. So their physical properties are they have low melting and boiling points, and they exist as gaseous diatomic molecules, or X2, so X subscript 2. And the physical states go from gas, liquid to solid as you move down the group, where bromine starts existing as a solid and chlorine is more gaseous. But this depends. It goes gas, liquid, solid all the way down the group, not just the first 3 elements. We look at our arrows again. It goes gas, gas, liquid, solid, solid. There. So the boiling point will increase because of their different structures. If it's a solid, then it will have more van der Waals forces than the gas. So therefore higher boiling points. And their electron configurations are also higher than most elements, as their outer shells are almost full. Like when you get down to astatine, and their redox reactions now are chlorine plus 2Br minus makes 2Cl minus plus Br2. CO2 plus 2I minus makes 2Cl minus plus I2. So chlorine is reduced and bromine is oxidized. So all elements are 0. Ions are the same charge, and again ions are charges, but elements are 0 at the end here. So bromine oxidizes I minus ions only. So bromine aqueous plus 2I minus makes 2Br minus plus I2, or iodine. Now, what you just looked at was a displacement reaction. It's when they form solutions and they displace other ions. The definition for it is a reaction in which more reactive elements displace less reactive element from an aqueous solution of the latter's ions. So what that basically means is if I had some bromine, for example, like here, then it would displace the chlorine here and make the chlorine ions and the bromine here, but it only oxidizes I minus ions. So we'll look at disproportionation. This is basically when the same element is both reduced and oxidized. So this bleach one is a very common example, and it's used quite a lot. Cl2 plus H2O equals HClO plus HCl. Chlorine is reduced, chlorine oxidized. Disproportionation of chlorine in aqueous sodium hydroxide. Now, this can make sodium chloride and bleach, and then water. So chlorine is both produced and oxidized. And finally, we move on to their uses in halogens' uses in halide tests. So, quick reminder: they are diatomic molecules. They have simple and molecular weak van der Waals forces between each diatomic molecule, and their oxidizing agent goes half of that the halogen plus E minus equals a halogen 1 minus ion, and halogen plus electron equals a halide ion, and their reactivity decreases down the group. I repeat, reactivity decreases down the group. Not increases like group 2, but it decreases down the group. With fluorine being the most electronegative, it's only logical to assume that all the others are weaker down the group, because fluorine is the most powerful oxidizing agent in the periodic table. So halides are sodium chloride, which is a common salt, sodium fluoride. They all have a 1 minus charge, and they're very, very stable. That's basically what they are. Sodium chloride, very, very, very stable because it has a 1 minus charge. Has no charge, and calcium fluoride has no charge either. Oh, no charge. And halide test results, these things you really do have to remember, and they can cost you a lot of marks, usually 2 or 3, so it pays to know them well. So chlorine, bromine and iodine. So silver, use silver nitrate in order to have silver ions present in order to react with the halide ions. So silver ions plus chlorine ions give silver chloride, and it makes a white precipitate, and it's soluble in dilute ammonia. If you'll notice, iodine does not dissolve in ammonia, and it has a yellow precipitate. So if the yellow precipitate stays in concentrated ammonia, then iodine is present. If bromine is soluble in concentrated NH3, then it is present. It's just another way of making sure that the ion is not iodine, basically. So it's practically the same. Silver plus Br minus equals silver bromide. Silver plus iodine equals silver iodide. So this is a precipitation reaction. A precipitation reaction takes place in aqueous solution when aqueous ions react together to form a solid precipitate. And here's a picture of what they all look like. So if you have that kind of picture in your head, then that'll be useful in exams and stuff like that. And here's some revision summaries for periodic trends. So as you go down the period, the shells increase, the shielding increases, the atomic radius increases, and the first ionization energy decreases. And as you go across the periodic table, the number of protons increase, the first ionization energy increases, and the atomic radius decreases. And now we zoom out and look at the trends in melting and boiling points. The second you hit giant covalent, that's at the very, very high melting point, and as you gradually get to the diatomic gaseous simple molecular lattice structures like phosphorus, sulfur, chlorine and argon, then you have relatively lower boiling points than the giant metallic lattices and elements like carbon and silicon. Now, these are the two group summaries that were on the previous 2 pages, and this is a summary of disproportionation. This might be useful for your notes. Anyway, that's the end of this tutorial. I hope you found this useful. We'll go through some more practice questions when I get round to them. So thank you for watching, and goodbye.
Bang.